So, big O, what is it and why do we need it? So we really want to pay attention to big O for a couple reasons. So first off, we want to pay attention to time and space efficiency. So if you solve a problem and it takes infinite time or infinite space, you're not really solving the problem. So we want to make sure that our problems can be solved in a reasonable amount of time. Big O gives us a language for which to analyze this. And secondly, is it gives us a way to compare two different algorithms. So for example, we might have a couple different algorithms for sorting. Which one is better? Which one should we use given a particular instance of a problem? And so big O gives us a language to do that. So what is big O anyways? So let me just say this is why big O. And then big O itself is concerned with, in the worst case scenario, what's the longest an algorithm might take. And this is going to be in terms of algorithmic steps. Right? And so these are operations. So we don't really care if we're adding two numbers or multiplying two numbers, right? Algorithmic steps include math, arithmetic, printing, but not function calls are dangerous because we don't know what goes into them. So ifs, but the real key here, and I'm going to colorize it for emphasis, is repetition. We care about repetition in the big O. What are the sources of repetition? And so the idea is that we really count the repetition. And so that's not just, the big O is not just in the worst case, the longest an algorithm can take as the input grows. As the input size grows is really what we care about. And so to that end, we care about repetition in terms of loops or recursion. That's really what we care about. Everything else becomes a constant. All this stuff here, these are constants. So we're really counting these algorithmic steps in terms of the repetition. So it's repetition, loops or recursion with respect to the size of the input data structure. Okay, awesome. And so let's kind of look at what this looks like for a couple different examples. So I don't have examples here. What I want to show you is how big O grows. There are examples on the worksheets. So here, what I want to show you are some examples of how these functions grow. Although I guess, let me bound it first. I do have a little bit of space here. Let me give you a quick example so you can see what I mean. So let's say we have a function. And we've got a function. Actually, I'm going to do a loop. Scratch that. Let's do a loop. So for I in range of n, print I. And then let's do for I in range 5, print I. And then lastly, for I in range x, for I in range x, print I times j. So I made the second I a j. Okay, so we've got three different functions here, and we want to think about what the big O looks like for these. Okay, so if we're doing just for I in range of n, we are going to repeat this print line of code n times. So this is going to be O of n. Now let's take this and say this whole example. I'm for I in range of 5, print I. Well, guess what? In this example, actually, let me erase this for a second. I'm just doing this example. For I in range of 5, I'm doing O of 1. Okay, where are these numbers coming from? Well, in the second example, I don't have any unbound variables. What does this mean? I don't have any variables that are unbound or undefined. Everything is fully specified. I know exactly what I'm printing. I could write this out by hand, what it looks like. And so it's not actually, this is gonna be 5 steps. But in big O notation, we actually don't care about any of the constants. So in big O, we throw away constants. Okay, so I'm gonna throw away constants. And so instead of this being O of 5, it's actually O of 1. Let's go back up to our previous example, for I in range of n. N, I can't tell you how many times this will execute, or how many times this loop will repeat. Since I don't know how many times this loop will repeat, then I'm big O of whatever isn't repeating. And so we assume that if there's something that's unspecified, like n or maybe x, that we are going to call that O of n. Now I am still printing. In fact, I could be printing twice. That is not going to affect the big O, because printing twice is a constant time operation. I can tell you how long that will take in advance. All right, so finally, let's go to our last example over here. Here I have 2 loops, but one is inside the other. So this print, this is going to repeat O of n squared times, because the inner loop is O of n, and the outer loop is O of n, and then I multiply them together to get O of n squared. Okay. Now let's move on here. So we have a little base of understanding. So now we get into some graphing a little bit. So we were playing with functions. Let me go to black. Or actually gray isn't used here. We were playing with functions that were O of n and O of n squared. So if you see, O of n is here. O of n squared is over here. So in terms of growth, so here on we have our x-axis, and this is the n, or our input data structure. And then on the y-axis, this is the time in terms of the number of steps. So as you can see, that O of n squared grows way faster than O of n. Oops. Okay, so that means that if we have a problem of size 5, O of n is still going to take around 5. But if we have an n squared problem, then it's going to take around 25. So O of n squared, for every step up, we're going to grow hugely. And as you can see from these functions, we have n factorial, 2 to the n, and so these are going to grow even faster. So when we're looking for efficient functions, we want the smallest big O. Now the only other thing I can share with you about this that I think is important is that for big O, we want to find, it's the worst case scenario, but it also might not align in practice. So in theory, something might take 5 or 25 in the worst case. We don't always get the worst case. And so in practice, we might see something take 16 for both of these. And one's a big O of n and one's a big O of n squared. Because the particular case may not be that way. So this is the big O is the worst case. There's also things called big theta and big omega, which allow us to capture, it's still similar notation in that we drop constants, but it's for the average case and the best case. However, most people want to plan for the worst case scenario, so big O is the most popular.